Hello. So let's talk about orbits. So we have already derived the trajectory of motion, the differential equation, and then the trajectory of motion for a satellite orbiting about, for example, Earth, or a similar object orbiting about one of the planets. So what we had in our solution was 1 over r is equal to gm over h0 squared 1 plus epsilon cosine theta. Epsilon was our eccentricity, and h0 was our angular momentum. G was our universal gravitational constant, capital G, and m was our large mass. For example, the mass of Earth, and then epsilon was our eccentricity. So epsilon was ch0 squared, and if you recall, c was one of our constant when we solved the second order differential equation. So what we had was r0 v0 squared over gm minus 1 is equal to epsilon. Now the question is, that's what we want to talk about, how would r change with epsilon? So there are various cases that could happen. For example, you might ask, what if our epsilon goes to 0? This is one of the cases. So if epsilon goes to 0, what does it mean? If you look at this, the definition of epsilon, if epsilon goes to 0, it means that r0 v0 squared, again, r0 was the point that the satellite, for example, is injected into its orbit. r0 v0 squared, and v0 is initial velocity. If epsilon goes to 0, it means that r0 v0 squared over gm minus 1 is equal to 0. It means that v0 is the square root of gm over r0. And also, if you look at this, for example, this equation, if epsilon goes to 0, it means that 1 over r is gm over h0 squared. In other words, it means that r is a constant. So in polar frame, if r is a constant, that describes the equation of a circle. So if we have a circular orbit, if our satellite is placed in a circular orbit, then v0 is the initial velocity, is the square root of gm over r0. You can think about it this way. If we require the satellite to be placed to land on a circular orbit about Earth, then v0 and r0 are related in using this relationship. And v0 in this case is v circular. Okay, we have a circular orbit, and this is our v0. This is one case. Now, how about when epsilon goes to 1 and theta is equal to 180? So if for epsilon equal to 1, theta was equal to 180, cosine theta is going to be minus 1, and this term, right-hand side, goes to 0. Agreed? So if you look at this equation again, if 1 over r goes to 0, because 1 plus epsilon cosine theta for this case goes to 0, it means that 1 over r goes to 0 and r goes to infinity. So if we have this case for our orbit, then you could say that r goes to infinity for this theta equal to 180. Agreed? All right. This is another case. So for this case, you could say that r is not anymore a definite number, it's an infinite number. So the orbit is not anymore a closed orbit. Right? Okay. So now what if 1 plus epsilon cosine theta goes to 0? In other words, now what we are interested in is the cases where r goes to infinity, the orbit is not closed, but theta is not necessarily equal to 180. So you want to know if we have other orbits, or you can think about it, or better think about it as trajectories, where theta is not equal to 180 necessarily, but still we have r equal to infinity. So 1 plus epsilon cosine theta goes to 0, epsilon cosine theta is equal to minus 1 as a result, because this goes to 0. So epsilon is minus 1 over cosine theta. Alright, if you think about theta in polar frame, cosine theta as a number is a number between minus 1 and 1. And now we are excluding minus 1 and 1. So cosine theta is somewhere between the two. And if you look at theta between pi over 2 and pi, alright, for theta between pi over 2 and pi, cosine theta is between minus 1 and 0. So minus 1 over, say, half or negative 0.5 is going to be equal to positive 2. It's a larger number. It's a number always larger than 1, right? So, in other words, if you plot this trajectory, you get a hyperbolic trajectory. So it is a trajectory where for theta between pi over 2 and pi, you satisfy this condition, 1 plus epsilon cosine theta being equal to 0, which implies r goes to infinity. So theta between pi over 2 pi, epsilon larger than 1, r goes to infinity. We have hyperbolic trajectory. Alright, so now the last case scenario is when epsilon is between 0 and 1. If epsilon was between 0 and 1, then in fact r is always bounded and we get an elliptical orbit. So you can show that if epsilon was between 0 and 1, and for epsilon equal to 0, you get circular orbit. For epsilon between 0 and 1, r is bounded, and in polar frame, you get an elliptical orbit. If you think about it in terms of velocity, for an elliptical orbit, v0 should be larger than the circular velocity, but be smaller than the velocity, which is called the escape velocity. Right? And the escape velocity, you can show that is the minimum velocity required to have an open trajectory rather than a closed orbit. So again, to remind you, if you have circular orbits, elliptical orbits, they are closed orbits, and then we have parabolic and hyperbolic trajectories. You can show that this velocity is the required escape velocity to have a parabolic trajectory. Thanks for paying attention.